guys, this is the end of day 2 notes. I remember we didn't get to the end and I couldn't remember if we finished this example, so I figured I'd just do them both in this video. So you can fast forward if you feel like you have example 6 down. In example 6, it asks us to first find the relative minimum. To find the relative minimum, we first want to find the critical values. The critical values are where the derivative equals 0. So when I'm looking at my derivative equation, there's a 0, and there is an undefined. I should say 0 or undefined. We had talked about that in class, I remember. So our critical values are -1, 3, and 7. From there, we're looking to see what is happening on either side of those critical values, because if it is coming from decreasing to increasing, we'll have a minimum. If it's going from increasing to decreasing, we'll have a maximum. So we just need to see which way we think the concavity is going. So let's look at each of these critical values. At -1, you can see it's got a positive slope here, and then it's going to a negative slope. So that one will be a maximum. At 3, you can see we have a negative slope, and it's turning positive to a positive slope, so that will be a minimum. And here where it's undefined, it's going from positive to positive, so this one is going to be a neither. It's neither a min or a max. So to answer the question, the only minimum value that we have is x equals 3, because it changes from negative slope to a positive slope. That would be our justification. And that's using the first derivative test, because we used the first derivative to check the critical values, and then we checked for the slope on either side. That was actually what we also did in day 1, so that one should look familiar. Relative max, we already kind of answered that. That's going to be at x equals -1, because it's going from increasing slope to a decreasing slope. But they want us to use the second derivative test. The second derivative test is just where you're looking at the second derivative to see if it's positive or negative. If it's 0, it's inconclusive, and we can't use the second derivative. We would have to go back to using the first derivative test. But let's see what's happening at -1 here. At -1, notice our second derivative of -1 is negative. Since it is negative, that is another confirmation that this is a relative max. Because if the second derivative is negative, that means it's going to be concave down, making it a relative max. Remember, the second derivative tells us the concavity. If it's negative, we know it's concave down. If the second derivative is positive, it's going to be concave up, giving us a relative minimum. Identify all the values of f that have a point of inflection. So to find the points of inflection using our second derivative test is we're looking for where f prime is equal to 0, and we're looking for sign changes on either side of it. Another thing with this problem is we're having to make the assumption this is continuous if this problem should say it's continuous. So let's make the assumption that it's continuous on this line. Okay. So it is 0 only here. Okay. So that is a potential point for a point of inflection. All we have to do is check on either side if it's changing from negative to positive or positive to negative. And if you look at the second derivative on either side, it's going from negative to positive. And therefore, we have a point of inflection at x equals 1, because the sign does change. It can positive, negative, negative, positive, and that'll be a point of inflection. Okay, the last one is the equation of the tangent line, and I feel like we for sure answered this one in class successfully. The point is 5 and 3. The slope at 5, so we would look at the first derivative at 5, and that is 2. So our equation is y minus 3 equals 2x minus 5. the last part is using tangent lines to make approximations. We've been using our tangent line to approximate points here. And if our tangent line is on top of this curve, if it's concave down, this is a concave down graph, our approximation will probably be a little bit high because the tangent line is on top of the curve. If our graph is concave up, we can assume that our approximation is going to be a little bit under of an estimate because it's going to be below that curve. This is the actual value, right? We're using the tangent line to estimate, and it's below it, so we can expect our estimate to be a little bit low. Okay, example 7 is just continuing some more examples from what we've been studying. Notice it says that f of x is continuous. That's what I was hoping the last one would say. It has to say continuous. Whenever we're given a table, from a graph you can see if it's continuous, or an equation you know it's going to be continuous because it's a quadratic or a cubic. When we're given a table, they really should specify is it continuous or not. Okay, and we have the first and second derivatives given to us here. For each x equals -5 and -2, so we're looking at these 2 points, -5 and -2, determine if the graph has a local minimum, local max, or neither. So we're going to start by looking at the second derivative because that can help us determine local maxes or mins. So if I look at the second derivative of -5, remember I only care if it's positive or negative because if it's negative, concave down, we have a max. If it's positive, it's concave up and we have a minimum. So I'm going to look here at -5, and since it equals a negative value, this tells us we have a local, let's see, concave down. So we have a local max at x equals -5 because it's concave down. For -2, okay, at -2, it's 0. So if it's 0, that means that this is inconclusive. We can't determine it from the second derivative because if it's 0, we don't know if it's going to be a max or a min. So in that case, we look at the first derivative instead. So let's look at the first derivative here. On the first derivative, remember, we're looking on either side to see if it has a sign change. Well, my slope is going from a negative slope, to a positive slope. So this tells us it's going to be a min at x equals -2 because the sign changes from negative to positive. So sometimes the second derivative test is not helpful if we have a 0 there. Okay, find any classify any additional known values of x or f of x has a relative extrema. So we already did this one and we did this one. At 3, we really don't have enough information because 0 or does not exist doesn't help us from the second derivative. When we go to the first derivative, I know it's increasing here, but what's happening here? So I really don't know what's happening at 3. I don't have enough information from the table here. Let's look at 11. Okay, the second derivative test fails us because it's 0, so that's not going to help us. So I go to the first derivative test, and I don't know what's happening to the left at that point. It's increasing over here, but I don't know what's happening here. So based on this table, we don't have any more information. No other critical values based on info given. We don't have any additional extrema based on what we know. At which values of x must the graph have a point of inflection? Okay, so to find the point of inflection, we're first going to look at our second derivative and look for zeros, because that's going to help us find the critical values. And then we'll see on either side, is there a sign change of those zeros? Okay, so on the second derivative, not there. Here we have one at -2. And we have a does not exist, but it has to be 0. So 0 and 0. So f prime of 11. Okay, so we found our zeros. Now we're going to look on either side for a sign change. Here we have a sign change from negative to positive. So that means we have a point of inflection at x equals -2. And let's check 11. We have a sign change from negative to positive, and x equals 11. We have points of inflection at -2 and 11 because the sign changes on either side of the zeros here. Okay, last question. Line tangent to the graph at x equals 6 is used to approximate f of 10. Will this approximation be an over or an underestimate? So this comes back to what we were talking about at the very beginning. So that'll kind of summarize this. Okay, so first we're going to find the, okay, we don't have the tangent line, but it's okay. What we're going to do is really what we need to know is there is a tangent line. If I know if the graph is concave up or concave down, I will be able to see if that tangent line is an over or under approximation based on these pictures right here. So what I want to do is at 6, looking at the double prime, because the double prime helps me figure out concavity, is it greater than 0 or less than 0? So I'm going to look at 6. Okay, so 6 falls in this range right here, which it is negative, so that's less than 0. So since it's less than 0, it's going to be concave down. So f of x is concave down. Therefore, these little dots mean therefore. That's a little math symbol you can use when you're writing math sentences. Therefore, the approximation will be an overestimate. Because when it's concave down, go back to this picture right here, my tangent line is going to be on top of it, so whatever my estimate is going to be an overestimate.